December 19th is not goodbye. It's not the moment when 3i Atlas vanishes from our story, disappearing into the cosmic backdrop like so many distant points of light. It's actually the beginning of something far more intriguing, a journey that stretches across distances most of us can barely comprehend, toward destinations we're only beginning to understand. And here's what makes this truly remarkable. We can predict where it's going with startling accuracy, yet there are elements of its path that remain frustratingly uncertain, variables that could shift its trajectory in ways that change everything we think we know about this visitor from beyond our solar system. That date, December 19th, marks the closest approach between 3i Atlas and Earth. It's the moment when this interstellar wanderer passes within our orbital neighborhood, close enough for our best telescopes to capture detailed observations, close enough for scientists to analyze its composition and behavior with unprecedented clarity. But while most attention focuses on that encounter, on that single moment of proximity, something far more fascinating is unfolding. The real story isn't about where it is on that date. The real story is about where it's going next, and what that trajectory might reveal about the nature of interstellar objects moving through our corner of the galaxy. Stay with me for the next several minutes, because we're going to trace the path of 3i Atlas from its December approach through the years and decades that follow, exploring not just the mechanics of its journey but the deeper questions it raises about purpose, randomness, and the patterns hidden within what appears to be chaos. Most people assume that when an interstellar visitor swings past Earth, it simply continues outward, drifting away on some arbitrary path determined purely by gravitational physics and momentum. And in the broadest sense, that's true. These objects aren't powered by engines or guided by navigation systems, at least not any we've detected. They move according to the fundamental laws of motion, responding to gravitational fields, following trajectories shaped by velocity and mass, and the invisible architecture of space-time itself. But here's where it gets interesting. The path 3i Atlas will take isn't entirely random. Its trajectory has structure, patterns, specific destinations it will pass through on its way back into the void between stars. And some of those destinations are worth paying very close attention to. NASA, ESA, and astronomical observatories around the world aren't just watching 3i Atlas for the sake of observation. They're tracking it because every interstellar object that passes through our solar system is a messenger, carrying information about stellar systems beyond our own, about the processes that shape planetary formation in distant corners of the galaxy, about chemistry and physics operating on scales we can't easily replicate in laboratories. When Oumuamua blazed through in 2017, it raised more questions than it answered, accelerating in ways that didn't quite fit standard models, leaving scientists scrambling to explain behavior that seemed almost deliberate. When Borisov arrived in 2019, it behaved more predictably, more like the comets we're familiar with, yet it too carried mysteries in its composition and structure. Now 3i Atlas arrives, and its chemistry alone has sparked intense debate, with spectroscopic analysis revealing methanol and cyanide in combinations that suggest either unusual stellar nursery conditions or something more complex, something that demands deeper investigation. So the question isn't just where it's going. The question is whether its path tells us anything meaningful, whether there's intention encoded in its trajectory, or whether we're simply watching physics play out in the void. And to answer that, we need to follow it beyond December 19th, beyond the moment of closest approach, into the months and years that stretch ahead. If this changes how you think about the objects moving through our solar system, if it makes you wonder what else might be out there traveling between the stars, hit that like button. Drop a comment telling me where you're watching from, and whether you think we're seeing pure physics or something that hints at deeper patterns. And subscribe, because as 3i Atlas continues its journey, as new data comes in and our understanding evolves, we'll be following every development, every unexpected turn in a story that's far from over. Here's what we know with certainty. 3i Atlas is moving on what astronomers call a hyperbolic trajectory. That's a technical term, but it carries enormous implications. A hyperbolic orbit means escape velocity has been exceeded. It means this object isn't bound to our sun's gravity, isn't caught in an elliptical loop that would bring it back centuries or millennia from now. It's moving too fast, carrying too much momentum, following a path that curves around the sun and then continues outward, never to return. Barring some catastrophic collision or gravitational interaction we haven't predicted, 3i Atlas will leave our solar system permanently. rejoining the interstellar medium from which it came, continuing a journey that may have started millions of years ago in a stellar system we'll never identify. That's the physics of it. The mathematics are clear, the trajectory models consistent across multiple independent calculations. But physics alone doesn't tell the complete story, because trajectories this precise, moving through gravitational fields this complex, are sensitive to factors we can barely measure. A slight outgassing event, releasing gas and dust from the comet's surface, could alter its path by fractions of a degree. A close encounter with a planet, passing through the gravitational influence of a gas giant, could bend its trajectory in ways that send it toward different regions of space than current models predict. Even the pressure of sunlight, the gentle push of photons striking its surface, accumulates over time, introducing tiny perturbations that compound across astronomical distances. So while we can say with confidence that 3I Atlas is leaving, while we can describe the general direction of its departure, the specific details, the precise path it will follow through the outer solar system and beyond, remain subject to variables we're still measuring, forces we're still quantifying. And that's where the mystery deepens, because some of those variables become most significant in the months immediately following its Earth approach. During a window when 3I Atlas will pass through regions of space where gravitational influences are strongest, where even minor interactions could reshape its ultimate destination. Scientists tracking the object aren't just recording its current position and velocity, they're building predictive models that extend decades into the future, simulating its path through gravitational fields, accounting for planetary positions and solar radiation pressure, and the subtle forces that act on any object moving through space. These models give us a roadmap, a projection of where 3I Atlas will be in January, in March, in the years beyond when it crosses the orbits of outer planets and begins its true journey into interstellar space. But models are only as good as the data they're built on, and right now, as December 19th approaches, as telescopes focus their attention on this visitor, scientists are gathering the final pieces of information they need to refine those predictions, to narrow the uncertainty margins, to answer the question that drives this entire investigation: where exactly is it going? And that's not an academic question. It's not just about plotting points on a chart or satisfying scientific curiosity, because where 3I Atlas goes, the path it follows, might tell us something profound about the nature of interstellar objects, about the mechanisms that seed galaxies with organic chemistry, about whether the universe operates purely on random chance, or whether patterns emerge, whether there are processes at work we haven't yet recognized, whether the chemistry we've detected and the trajectory we're observing might be connected in ways that challenge our assumptions about what's natural and what's not. But first, before we can explore those deeper questions, before we can trace the path ahead and examine what it might mean, we need to understand what happens immediately after December 19th, what forces will shape the journey in the critical months that follow, and why certain dates, certain orbital positions, matter far more than simple distance would suggest. Think of the solar system as a highway interchange, a place where gravitational roads converge and diverge, where objects can enter, pass through, and exit along paths determined by speed and trajectory, and the warping of space around massive bodies. Most of what we see, the planets and asteroids and comets that make up our cosmic neighborhood, are traveling on circular or elliptical routes, bound to the sun, caught in orbital patterns that repeat endlessly. They're commuters on a loop, circling the same stretch of highway forever. But 3I Atlas isn't on that kind of path. It's traveling the express lane, the route that doesn't loop back, the trajectory that leads away from the interchange and out into the open road of interstellar space. That's what a hyperbolic orbit means in practical terms. It's an escape trajectory, a path that curves around the sun as the object falls inward, accelerates through perihelion, and then continues outward with enough velocity to overcome the sun's gravitational pull permanently. Imagine throwing a ball into the air. If you throw it gently, it rises and falls back into your hand, completing a parabolic arc. Throw it harder, and it rises higher before returning. But if you could throw it fast enough, if you could give it sufficient velocity, it would rise and keep rising, never falling back, escaping Earth's gravity entirely. That's escape velocity. And 3I Atlas has exceeded the solar system's equivalent, moving at speeds that ensure it will never be pulled back, never return to orbit our sun, never complete a closed loop. The numbers tell the story, though we don't need to dwell on precise figures to grasp the implications. What matters is that 3I Atlas entered our solar system, carrying the momentum of interstellar space, moving at velocities characteristic of objects in the galactic medium, and as it fell toward the Sun, as it passed through the inner solar system, it accelerated further, gaining speed through the Sun's gravity in a process that works like a gravitational slingshot. By the time it reaches perihelion, the closest point to the Sun in its trajectory, it's moving faster than when it arrived, and that additional velocity ensures its escape, guarantees that it's on a one-way journey outward. We've seen this before. Oumuamua, the first confirmed interstellar object detected in our solar system, followed a similar path, entering on a hyperbolic trajectory, passing near the Sun, and then departing along an escape route that carried it back into deep space. Borisov, the interstellar comet discovered in 2019, did the same, approaching, swinging around the Sun, and then continuing outward on a path that would never bring it back. These aren't unusual events in cosmic terms. The galaxy is filled with rogue objects, materials ejected from stellar systems during planetary formation, comets cast out by gravitational interactions, fragments of worlds that never fully formed. They drift through interstellar space for millions of years, occasionally passing through other solar systems, briefly illuminated by alien suns before continuing their endless journeys. Our solar system is simply one node in that vast network, one intersection where these travelers occasionally pass through, and 3I Atlas is the latest we've been fortunate enough to detect. But here's where the story gets more complex, where the simple narrative of it came, it passed, it's leaving, starts to show cracks. Because while the general shape of the trajectory is clear, while we know 3I Atlas is on an escape path, the specific route it will follow depends on factors that are still unfolding, forces that will act on it in the months ahead, gravitational interactions that could subtly alter its course and change where it ultimately goes. Space isn't empty. It's a web of gravitational fields, regions where massive bodies warp space-time, creating slopes and curves that affect anything passing nearby. When 3I Atlas moves through the inner solar system, it's navigating a complex landscape shaped by the Sun's gravity primarily, but also influenced by planets, especially the large ones, the gas giants whose mass creates significant gravitational presence even at considerable distances. Most of the time, these influences are negligible, tiny perturbations that barely register in trajectory calculations. But there are moments, specific windows when orbital mechanics align, when an object's path brings it close enough to a planet for that gravitational interaction to matter, for the curve of space-time around that world to bend the object's trajectory in measurable ways. And that's the key to understanding where 3I Atlas goes next. Its path after December 19th isn't fixed in stone. It's a probability cloud, a range of possible trajectories determined by how precisely we've measured its current motion and how accurately we can predict the forces that will act on it. Small uncertainties now become large uncertainties over time. A deviation of a fraction of a degree at the beginning of the journey translates into differences of millions of kilometers decades later. So when scientists build models projecting where 3I Atlas will be in 2050 or 2080, they're working with ranges, with confidence intervals, with predictions that become less certain the further into the future they extend. But there are moments in the near term, specific events in the months following December 19th, where those uncertainties could resolve in one direction or another, where the trajectory could shift in ways that determine which region of space 3I Atlas ultimately travels toward. And one of those moments involves Jupiter, the solar system's largest planet, a gravitational powerhouse whose influence extends far beyond its physical boundaries. We'll explore that interaction in detail, but for now, what matters is understanding that 3I Atlas isn't just coasting through empty space. It's navigating a gravitational landscape, responding to forces that will shape its path, and some of those forces become most significant not during its close approach to Earth, not at perihelion when it's nearest the Sun, but in the months that follow, when it moves through regions where planetary gravity becomes the dominant influence, where interactions we're still calculating could determine the course of its journey for millennia to come. This is why scientists continue tracking it, why observatories around the world remain focused on this object long after the initial excitement of discovery fades, why the story doesn't end with December 19th but extends into 2026 and beyond. Because every observation refines the models, every measurement narrows the uncertainty, every data point brings us closer to understanding not just where it's going but why, not just the destination but the route, Not just the physics, but the implications of watching an interstellar visitor navigate our solar system's gravitational terrain. The solar system is a crossroads, and 3I Atlas is passing through. But crossroads are places where paths diverge, where choices are made, where direction matters. And in the case of this object, in the specific circumstances of its trajectory and timing, there's one particular intersection ahead that could prove more significant than any other. One gravitational encounter that might reshape our understanding of where this journey leads, and what it might mean for the nature of interstellar objects moving through our corner of the galaxy. Speaking of which, we need to talk about Jupiter. After December 19th, after the moment of closest approach to Earth, 3I Atlas doesn't simply fade into the cosmic background. It continues its outward journey, moving through specific regions of the night sky, tracing a path that astronomers can predict with reasonable accuracy, crossing constellations and orbital planes as it accelerates away from the inner solar system. For the first few months of 2026, it remains visible to powerful telescopes, still bright enough for spectroscopic analysis, still close enough for detailed observation. But visibility is a temporary gift, and with each passing week, the window narrows, the opportunity for gathering data diminishes. The moment approaches when 3I Atlas will move too far, grow too faint, and slip beyond the reach of even our most sophisticated instruments. In early 2026, it will move through regions of the sky that astronomers can track precisely against the backdrop of distant stars as it continues its outward trajectory. Over the following months, it will shift against the background constellations, moving through well-mapped star fields where astronomers can use precise astrometry to refine its position and velocity measurements. These observations matter enormously because every data point collected during this window helps constrain the trajectory models, helps narrow the range of possible paths it might follow in the years ahead. Miss this opportunity, let it slip away without thorough observation, and we lose the chance to answer questions that might not have another opportunity for resolution until the next interstellar visitor arrives, and we have no idea when that might be. But it's not just about observation for observation's sake, it's about timing, because March 2026 represents a critical moment in the journey of 3I Atlas when orbital mechanics bring it into a relatively close pass by Jupiter, the solar system's largest planet, a gravitational giant whose influence can measurably bend trajectories, even across tens of millions of kilometers. Now, proximity in astronomical terms doesn't mean collision or even particularly close approach. The distances involved are still enormous by human standards, on the order of tens of millions of kilometers separating the comet's path from Jupiter itself. But gravity doesn't require contact to exert influence. It operates across distances, its effects diminishing with range but never truly disappearing. And for an object on a trajectory that brings it into the region of space where Jupiter's gravitational field is significant, even a distant encounter can produce measurable effects. This is why March 2026 matters. This is why scientists are focused not just on December's Earth approach, but on the months that follow, on the specific window when 3I Atlas will move through the outer solar system's gravitational landscape, where Jupiter's mass creates a significant warp in space-time, where the trajectory could bend in ways that alter the object's ultimate destination. Whether that bending actually occurs, whether the encounter is close enough, and the gravitational gradient steep enough to produce detectable changes, depends on precise measurements we're still refining, on trajectory calculations that carry uncertainty margins we're working to reduce. But the possibility exists, and with it comes a fascinating question. If 3I Atlas's path does bend during that March encounter, if Jupiter's gravity does exert influence, where would the new trajectory point? Right now, based on current trajectory models, 3I Atlas is on a path that will carry it out of the solar system, in a specific direction, toward a particular region of the galaxy we can describe in terms of galactic coordinates, toward a destination decades and centuries away that represents the natural continuation of its inbound trajectory adjusted for solar gravitational effects. But if Jupiter alters that path, if the gravitational interaction introduces changes in velocity or direction, the destination could shift. The object could end up traveling toward a different region of space, and the question becomes whether that shift is random, purely a function of orbital mechanics and timing, or whether there's any pattern to it, any reason to think the March encounter might be more than just coincidental. That might sound like speculation, like reading too much into what's essentially a predictable gravitational interaction between a comet and a planet, and maybe it is. Maybe the March 2026 proximity to Jupiter is purely coincidental, an accident of timing that has no deeper significance, a gravitational encounter that will produce subtle effects we can measure, but that don't indicate anything beyond standard physics playing out in the void. But there's another perspective worth considering, one that takes into account the unusual chemistry of 3I Atlas, the methanol and cyanide detected in its spectrum, the organic compounds that could be relevant to prebiotic chemistry, the possibility, however remote, that this object carries more than just rock and ice on its journey through the galaxy. Because if you were designing a mission, if you were an intelligence trying to seed organic chemistry across stellar systems, if you had the capacity to send objects on interstellar trajectories, and you wanted to maximize the chances of those objects reaching interesting destinations, you'd pay attention to gravitational assists. You'd time your approach to coincide with planetary positions that could alter your trajectory in useful ways. You'd use the solar system's own gravitational architecture to redirect your path toward targets that matter, toward locations where the chemistry you're carrying might have the greatest impact. And in our solar system, one of the most interesting targets, one of the places where organic chemistry and liquid water and energy sources converge in ways that could potentially support life, isn't Earth. It's Europa, Jupiter's ice-covered moon, a world with a subsurface ocean larger than all of Earth's seas combined, a place where hydrothermal vents might create the same kind of chemically rich environments that gave rise to life on our own world billions of years ago. Now, before we go further, let me be absolutely clear. This is speculation. There's no evidence that 3I Atlas is guided, no indication that its trajectory is anything other than natural, no reason to think it's targeting Europa or any other specific destination. The overwhelming likelihood is that we're watching physics, nothing more. A comet on a gravitationally determined path that happens to pass near Jupiter because that's where orbital mechanics placed it, not because of any intentional design. But the timing is interesting. The chemistry is interesting. The fact that March 2026 brings 3I Atlas into Jupiter's neighborhood, into the region where Europa orbits, into a position where gravitational effects could potentially alter its trajectory in ways that point toward one of the solar system's most astrobiologically significant locations, that's worth noting, worth thinking about, worth keeping in mind as we follow this object's journey and watch for anything unexpected. Astronomers will be watching carefully during that window. The James Webb Space Telescope, with its infrared sensitivity and unprecedented resolution, could potentially observe 3I Atlas even as it moves into the outer solar system, tracking its position against background stars with the precision needed to detect subtle trajectory changes. Ground-based observatories, equipped with adaptive optics and large apertures, will contribute their own observations, building up a comprehensive picture of the object's motion, capturing data that can be analyzed for any deviations from predicted paths, any accelerations or course changes that might indicate influences we haven't accounted for. And radio telescopes, sensitive to emissions across a broad spectrum, will listen just in case there's anything to hear, any signal or transmission or indication of activity that goes beyond what we'd expect from an inert chunk of rock and ice. Most likely, they'll find nothing unusual. Most likely, 3I Atlas will follow a trajectory determined purely by gravity and momentum, passing Jupiter's orbital region without incident, continuing outward on a path that matches predictions, behaving exactly as an interstellar comet should behave. But science advances by checking, by observing, by gathering data, even when you expect it to confirm what you already think you know, because occasionally, the universe surprises us. Occasionally, objects don't behave quite as predicted, and occasionally, what looks like random chance turns out to have structure, pattern, meaning hidden beneath the surface. As we move into 2026, as March approaches and 3I Atlas reaches that critical window near Jupiter, the scientific community will be paying close attention, not because they expect miracles, not because they're hoping for evidence of artificial guidance, but because this is what we do. We observe, we measure, we test our models against reality, and sometimes, rarely, reality pushes back, showing us something we didn't anticipate, something that forces us to reconsider our assumptions and expand our understanding of what's possible in a universe far stranger and more complex than we often imagine. But if Jupiter did alter its path, if that March encounter produces detectable changes in trajectory, the next question becomes, where would it point? And what might that destination tell us about the nature of this visitor and the journey it's been on long before it ever reached our solar system. Gravitational assists aren't magic. They're physics, well understood, and routinely exploited by spacecraft engineers, who need to send probes to the outer solar system without burning impossible amounts of fuel. The principle is simple. Use a planet's gravity and orbital motion to change a spacecraft's velocity and direction, effectively stealing a tiny amount of the planet's momentum and transferring it to the spacecraft. Voyager did this, swinging past Jupiter and Saturn and using each encounter to accelerate toward the next destination, ultimately achieving the velocity needed to escape the solar system entirely. Cassini did it, performing multiple flybys of Venus and Earth before reaching Jupiter for a final boost towards Saturn. Every mission to the outer planets uses this technique, because the alternative, carrying enough fuel to make those journeys using propulsion alone, is prohibitively expensive and technically impractical. The physics works because planets are moving, orbiting the Sun with tremendous velocity, and when a spacecraft approaches from the right direction at the right time, it can fall into the planet's gravitational well, whip around behind it, and emerge on the other side with its velocity increased, its trajectory altered, its momentum boosted by an amount that would require enormous fuel expenditure to achieve through propulsion. It's elegant, efficient, and entirely natural, in the sense that no special technology is required beyond the ability to navigate precisely and time the encounter correctly. Gravity does the work. The planet's motion provides the energy. The spacecraft just has to be in the right place at the right time. Now, here's the interesting part. This process isn't exclusive to spacecraft. It happens naturally, all the time, throughout the solar system and beyond. Comets can receive gravitational assists from planets. Asteroids can have their trajectories altered by close encounters with Jupiter or Saturn. Rogue planets wandering through the galaxy can be accelerated or decelerated by stars they pass. The universe is full of gravitational interactions, producing effects that redirect objects, change velocities, alter destinies. We call it a gravitational assist when humans do it deliberately, when spacecraft engineers plan the encounter and execute the navigation needed to achieve the desired outcome. But the physics doesn't care about intention. It operates the same way whether the object being affected is a human-made probe or a natural chunk of rock and ice traveling through space. So the question isn't whether 3I Atlas could receive a gravitational assist from Jupiter. It absolutely could, if the geometry is right, if its trajectory brings it close enough to the planet at the right angle, if the timing aligns to produce the necessary interaction. The question is whether it will, whether the March 2026 encounter represents a close enough approach for Jupiter's gravity to produce measurable effects, and if so, what those effects might be, how they might alter the object's path, and where the new trajectory would lead. Current models suggest the encounter will be distant enough that any gravitational influence remains small, well within the uncertainty margins of our trajectory predictions, potentially detectable with precise observations, but not dramatic enough to radically reshape the object's path. But models are built on measurements, and measurements carry uncertainties, and those uncertainties compound when you're dealing with objects moving at interstellar velocities through complex gravitational fields. A small error in our current velocity estimate, a slight miscalculation of the object's mass or how solar radiation pressure affects its trajectory, could mean the difference between a distant pass and a more significant interaction, between negligible effects and changes that redirect 3I Atlas toward a meaningfully different destination. What would we look for? How would scientists detect a gravitational assist in progress? The answer lies in precise position measurements over time, in tracking the object's location against the background stars with enough accuracy to detect deviations from predicted paths. If 3I Atlas passes Jupiter without significant interaction, its trajectory will continue smoothly along the path we've calculated, its position matching predictions, its velocity remaining consistent with models. But if a gravitational assist occurs, if Jupiter's gravity bends its path in measurable ways, we'd see discrepancies. The object would appear slightly off from where we expected it to be, arriving at predicted coordinates a little early or late, moving at an angle that doesn't quite match projections. Those discrepancies would be small initially, fractions of a degree, tiny velocity changes, but they'd accumulate over time, growing more pronounced as months pass, eventually resolving into a clear signal that something altered the trajectory during the Jupiter encounter. The engineering thought experiment becomes fascinating here. Imagine you're planning a mission, not with a spacecraft but with a comet, Using natural materials and gravitational physics rather than rockets and fuel, you want to visit multiple targets in a solar system. You're approaching from interstellar space, carrying momentum from your journey through the galaxy, entering along a hyperbolic trajectory that will take you past the sun and back out into the void unless you do something to alter that path. You don't have engines. You can't burn fuel to change course. But you can use gravity. If you're clever, if you time things right, if you navigate precisely enough to turn the solar system's own architecture into a guidance mechanism, you'd aim for the inner system first, passing close to the sun to maximize the gravitational acceleration you receive, building velocity for the outbound leg. But you wouldn't waste that velocity on a straight-line escape. You'd use it to reach a gas giant, one of the massive outer planets, whose gravity is strong enough to bend your trajectory significantly, to redirect you toward a target that matters, toward a moon or region of space, where the chemistry you're carrying might find an environment conducive to whatever process you're trying to initiate. And if that target happened to be Europa, if your goal was to deliver organic compounds to a subsurface ocean where liquid water and energy sources create conditions potentially suitable for life, you'd time your approach to Jupiter very carefully, using the planet's gravity not just to assist your journey but to redirect it, to change your outbound trajectory from one that leads back into interstellar space toward one that intersects with Europa's orbit, that brings you close enough for chemistry transfer, for material deposition, for whatever mechanism you're employing to seed that distant ocean with the building blocks of biology. Now, again, let me emphasize, this is speculation, a thought experiment, an exploration of what would be possible if 3I Atlas were something other than a natural comet on a random trajectory. There's no evidence for it. No observations suggest artificial guidance. No trajectory anomalies indicate propulsion or maneuvering. The overwhelming likelihood is that this object is exactly what it appears to be. A chunk of material ejected from another stellar system millions of years ago, now passing through ours on a path determined by gravity and momentum, nothing more. But the thought experiment is useful because it highlights what we should be watching for. What kinds of trajectory changes would be surprising? What patterns might indicate something more than just random physics? If 3I Atlas were on a mission, if its trajectory were designed rather than accidental, we'd expect certain characteristics. We'd expect precise timing, approaches to planetary bodies that maximize gravitational assist potential. We'd expect trajectory changes that point toward interesting targets rather than random directions. We'd expect chemistry that makes sense in the context of those targets, compounds that could play useful roles in prebiotic environments, materials that aren't just random but selected for specific purposes. And we'd expect efficiency, trajectories that achieve objectives with minimal energy expenditure, using natural gravitational processes rather than requiring impossible amounts of propulsion. Does 3I Atlas exhibit those characteristics? The timing is interesting. Arriving in our solar system when Jupiter's position allows for a close approach during the outbound leg. The chemistry is interesting, with methanol and cyanide that could be relevant to prebiotic chemistry in the right environments. The trajectory is interesting, following a path that brings it near Jupiter at a moment when gravitational influence could redirect it toward the Jovian moons. But interesting doesn't mean conclusive. Coincidence happens. Patterns emerge from randomness. The universe is large enough and complex enough that occasionally things align in ways that look meaningful even when they're not. What separates genuine structure from apparent pattern is evidence, data, observations that confirm or refute the hypothesis. And that's exactly what scientists will be gathering over the next several months, watching 3I Atlas as it moves through the outer solar system, tracking its position with the precision needed to detect any deviations from natural trajectories, looking not because they expect to find artificial guidance, but because ruling it out requires checking, because science advances by testing hypotheses against reality rather than assuming answers. But if Jupiter does alter its path, if that gravitational interaction produces changes we can measure, the implications extend beyond simple orbital mechanics and into deeper questions about what Europa represents, why it matters, and whether the chemistry 3I Atlas carries might be more significant than we initially realized. Europa doesn't look like much from the outside. It's a moon, one of dozens orbiting Jupiter, not even the largest, covered in ice that reflects sunlight with almost mirror-like intensity, crisscrossed by cracks and ridges that speak to tectonic processes operating beneath the frozen surface. But beneath that ice, Beneath kilometers of frozen water lies something extraordinary. An ocean, a genuine liquid water ocean, larger in volume than all of Earth's seas combined. Kept warm by tidal heating as Jupiter's gravity kneads Europa's interior, generating friction, producing heat, creating an environment where liquid water persists despite being so far from the sun that surface temperatures hover around -160 degrees Celsius. That ocean makes Europa one of the most astrobiologically significant locations in our entire solar system. Not because we found life there, we haven't. We've barely begun to explore what lies beneath that ice. But because it has the fundamental ingredients, liquid water, energy sources from tidal heating, and quite possibly chemical nutrients delivered by impacts or generated through interactions between the ocean and the rocky seafloor. On Earth, wherever we find liquid water and energy and chemistry, we find life, even in the most extreme environments imaginable, in boiling hot springs and frozen Antarctic lakes and deep ocean trenches where sunlight never penetrates. Life adapts, colonizes, persists. So the question isn't whether Europa could support life. The question is whether it does, whether that dark ocean circulating beneath the ice contains ecosystems we've never imagined, organisms adapted to an environment utterly alien to surface-dwelling creatures like ourselves. Now, compare Europa to Earth from the perspective of interstellar chemistry delivery. Earth is warm, bathed in sunlight, covered in an atmosphere that burns up most material falling from space before it reaches the surface. If you wanted to deliver organic compounds to Earth, you'd face atmospheric entry, heat that would vaporize or destroy fragile molecules, oceans and land masses scattered across a rotating sphere where most impacts would hit ocean or unpopulated areas, making targeted delivery nearly impossible. Earth is a difficult target, despite being the only location in our solar system where we know life exists. Europa, by contrast, is a simpler target in some ways. No atmosphere to burn up incoming material, a surface entirely covered in ice, no landmasses or dry areas to complicate delivery. An ocean directly connected to the surface through cracks and fissures where water occasionally erupts in cryovolcanic plumes, creating pathways through which surface materials can be transported into the subsurface environment. If you were trying to seed organic chemistry into that ocean, you wouldn't need to penetrate kilometers of ice through drilling or melting. You'd just need to deliver material to the surface near one of those active regions, near a crack or plume source, and let Europa's own geological processes do the rest, transporting your chemistry downward through natural pathways into the liquid water environment below. And here's where the chemistry of 3I Atlas becomes fascinating from this perspective. Methanol and cyanide aren't random compounds. They're both relevant to prebiotic chemistry, both potentially useful in dark ocean environments, where photosynthesis isn't possible, where life would need to derive energy from chemical reactions rather than sunlight. Methanol can serve as a carbon source, a building block for more complex organic molecules. And in cold environments like Europa's ocean, it remains liquid at temperatures where water would freeze, potentially acting as an antifreeze or solvent that enables chemistry to occur in conditions that would otherwise be too cold for molecular interactions. Cyanide, despite its reputation as a poison, is a crucial component in some prebiotic chemistry scenarios, capable of participating in reactions that generate amino acids and nucleotides, the building blocks of proteins and genetic material. If you were designing a chemistry package to deliver to a dark ocean environment, to seed a subsurface sea with compounds that could jumpstart prebiotic chemistry or support existing ecosystems, methanol and cyanide would be reasonable choices, practical compounds that remain stable during interstellar travel, that don't require complex molecules that might break down over millions of years in transit, that can participate in the kinds of reactions necessary for building more complex organic structures once they reach their destination. And if you wanted to deliver that package to Europa specifically, you'd need to approach Jupiter to enter the Jovian system's gravitational influence, to navigate close enough to Europa's orbit that your trajectory intersects with the Moon's path, or at least brings you close enough for material to be transferred through gravitational interactions or impact events. The March 2026 Jupiter encounter, viewed through this lens, becomes more than just a gravitational assist opportunity. It becomes a potential delivery window, a moment when 3I Atlas's trajectory brings it into the region where Europa orbits, where the possibility exists, however remote, for interaction between the comet and the Moon, for chemistry transfer through mechanisms we'd need to study in detail to fully understand. Maybe through direct impact, though the orbital geometries would need to align very precisely for that. Maybe through gravitational disruption, with tidal forces fragmenting the comet and scattering material across Europa's orbital path, where the Moon could sweep through it over subsequent orbits. Maybe through some mechanism we haven't considered, some process that becomes apparent only when we observe what actually happens during that encounter. To be absolutely clear, there is no evidence that any of this is happening. No observations suggest. 3i Atlas is targeting Europa. No trajectory data indicates artificial course corrections aimed at the Jovian system. No analysis of the object's behavior shows anything inconsistent with a natural comet on a gravitationally determined path. This is speculation, an exploration of possibilities, a thought experiment that asks what we might look for if this object was something other than it appears to be. Science requires this kind of thinking, this willingness to consider alternatives, to explore hypotheses, even when they seem unlikely, because occasionally the universe surprises us, and occasionally what seems impossible turns out to be the explanation that fits the data. But even as speculation, it's grounded in real orbital mechanics, real chemistry, real astrobiology. Europa is genuinely interesting, genuinely significant as a potential location for life beyond Earth. The compounds detected in 3i Atlas are genuinely relevant to prebiotic chemistry, genuinely useful in the kinds of environments that exist beneath Europa's ice. The timing of the Jupiter encounter is genuinely coincidental enough to raise questions, even if those questions ultimately have mundane answers. And the broader context matters. We live in a galaxy where stellar systems are separated by distances so vast that deliberate travel between them requires timescales and energy expenditures that challenge our capacity to imagine, where the only practical way to spread chemistry or biology across interstellar space might be through exactly this kind of mechanism. Using natural objects on natural trajectories, guided subtly through gravitational interactions rather than propulsion, seeded with compounds that remain stable over millions of years, and that can deliver their payloads when they encounter suitable environments. Whether 3i Atlas represents such a mechanism, whether it's carrying out a mission we're only beginning to recognize, remains to be seen. The observations over the next several months will be crucial. The trajectory data collected during and after the Jupiter encounter will tell us whether anything unexpected occurs, whether the path bends in ways that point toward Europa, or whether it continues outward on a trajectory indistinguishable from what we'd expect from a natural comet. Scientists will be watching, analyzing, comparing predictions to reality, and if discrepancies appear, if anything suggests this object is behaving in ways that challenge our models, the conversation will shift, the questions will deepen, and we'll face the fascinating possibility that interstellar visitors might be more common and more purposeful than we've dared to imagine. But whether or not Europa proves relevant, whether or not the March encounter produces anything surprising, one thing remains certain. 3i Atlas is leaving, continuing a journey that extends far beyond the Jovian system, far beyond the realm where planetary gravity matters, out into the vast emptiness, where the solar system gives way to interstellar space, and where the true scale of its journey becomes apparent. Beyond Jupiter lies territory that's technically still part of our solar system but feels fundamentally different from the crowded inner regions, where planets orbit close together and the sun's warmth makes worlds habitable. Out here, in the realm of the ice giants and dwarf planets, distances become almost incomprehensible. Orbits stretch across billions of kilometers, and the sun itself shrinks to a bright star, still the dominant light source, but no longer the overwhelming presence that defines existence in the inner system. This is where 3i Atlas will spend decades of its journey, crossing the orbits of Saturn, Uranus, Neptune, moving through spaces so vast that even traveling at interstellar velocities, it takes years to traverse the gaps between major landmarks. The timeline stretches out in ways that challenge human intuition. By the time 3i Atlas crosses Saturn's orbital distance, we'll be in the late 2020s, approaching the 2030s, nearly a decade beyond its discovery. A full human decade of continuous outward motion just to reach a point that's still well within the sun's gravitational influence. Uranus comes next, sometime in the 2040s, decades after anyone reading these words right now will have last heard the object's name in mainstream media, long after the initial excitement of discovery has faded, existing only in astronomical databases and the long-term monitoring programs that track interstellar visitors as they retreat into the darkness. Neptune, the outermost of the major planets, represents a milestone that won't arrive until perhaps the 2060s, a full 40 years from now, a time span longer than many human careers, longer than most people maintain interest in any single topic, yet still just the beginning of 3i Atlas's true journey. Because the solar system doesn't end at Neptune. Not even close. Beyond the orbit of the outermost major planet lies the Kuiper Belt, a vast region populated by icy bodies and dwarf planets, remnants of planetary formation that never coalesced into worlds, and beyond that, further still, lies the Oort cloud, a spherical shell of cometary material surrounding the entire solar system at distances so enormous that the sun's gravity barely holds them, where the space between objects is measured in astronomical units or even light years, where the boundary between solar system and interstellar space becomes fuzzy, defined more by convention than clear physical demarcation. The heliopause, the point where the sun's influence finally gives way to the interstellar medium, where the solar wind collides with the galactic background and creates a boundary that spacecraft like Voyager have crossed, lies somewhere beyond 100 astronomical units from the sun, a distance that 3i Atlas won't reach for decades, perhaps not until the 2090s or later, depending on its exact velocity and trajectory. Voyager 1, traveling at impressive speed for a human-made object, took 35 years to reach the heliopause after leaving Earth. It's now in interstellar space, still transmitting data back to us, still traveling outward at a pace that will carry it light years from the sun over the coming millennia. 3i Atlas will follow a similar journey, though on a different trajectory, moving at comparable or slightly higher velocities, crossing that same boundary between solar and interstellar space sometime late this century, assuming we're still tracking it by then, assuming we haven't lost it to distance and darkness and the limits of our telescopes. What happens to an object during those decades of travel? Not much, in the dramatic sense. Space is mostly empty, even in the Kuiper Belt and Oort cloud, where objects are sparse and collisions rare. 3i Atlas will coast, moving on momentum, following the trajectory shaped by its perihelion passage and any gravitational encounters along the way, gradually fading as distance increases, growing colder as the sun's warmth diminishes, becoming less and less active as the materials that once outgassed near the sun freeze solid in the deep cold of the outer system. It becomes, essentially, a frozen relic, a chunk of ice and rock and chemistry traveling through darkness. No longer the bright comet that captivated observers during its inner system passage, just another piece of cosmic debris on an interstellar trajectory. But it leaves something behind. The chemistry that outgassed during its approach, the methanol and cyanide and other compounds released when solar heating warmed its surface. Those molecules don't travel with the main body. They disperse, spreading out along the trajectory, forming a diffuse wake that extends behind the comet like a trail marker, a chemical signature that persists in space long after the object itself has moved on. Where do those molecules go? They drift, carried by solar wind and radiation pressure, mixing with the interplanetary medium, eventually dispersing so widely that their concentrations become undetectable, indistinguishable from the background chemistry of space. Some might eventually reach Earth or Mars or other worlds, arriving years or decades later, integrated into the constant rain of interplanetary material that falls onto planetary surfaces, contributing their tiny fraction to the chemical inventory of those worlds. Could we track that wake? Could we follow the trail of chemistry that 3i Atlas leaves behind, mapping where those molecules go, measuring how they disperse, understanding what happens to organic compounds released in the outer solar system? In principle, yes. With sufficiently sensitive instruments and dedicated observation programs, scientists could monitor the chemical wake, detecting spectroscopic signatures of methanol or cyanide in the space along 3i Atlas's trajectory, watching as those signatures fade and spread over time. In practice, it's challenging, requiring resources and telescope time that might be better spent on other projects, especially as the concentrations diminish and the signal-to-noise ratio drops. But the data would be valuable, adding to our understanding of how chemistry moves through space, how organic compounds disperse and survive in the harsh environment of the solar system, how material exchange occurs across astronomical distances. Monitoring continues, not continuously, but periodically, as opportunities arise and scientific interest warrants. Radio telescopes might observe 3i Atlas at intervals, checking for any unexpected emissions, any signals that could indicate activity beyond simple outgassing. Optical surveys might capture it in images, tracking its position against background stars, refining trajectory models as more data accumulates. Infrared telescopes, particularly space-based instruments like James Webb, could potentially observe thermal emissions, detecting heat signatures that reveal information about the object's composition and internal state, even as it retreats to distances where visible light becomes too faint to measure effectively. We're watching for surprises, for anything that doesn't fit expectations, for behavior that challenges our understanding of what an interstellar comet should do. Most likely, there will be no surprises. Most likely, 3I Atlas will behave exactly as predicted, following its trajectory without deviation, outgassing according to standard models, exhibiting no characteristics that suggest anything beyond natural processes. But science requires checking, requires observation, even when you expect routine results, because occasionally objects do surprise us. Occasionally, something unexpected happens. Oumuamua accelerated in ways that took years to explain, sparking debates about outgassing mechanisms and non-gravitational forces, and whether conventional models fully captured its behavior. Borisov fragmented slightly during its passage, breaking into pieces that complicated trajectory predictions and raised questions about structural integrity. 3I Atlas might do something similar, might exhibit behavior we haven't anticipated, and the only way to catch those surprises is to watch, to observe, to maintain the monitoring programs that track these visitors as they pass through our solar system. And that brings us to the real answer, the ultimate destination, the place where 3I Atlas is really going after all the gravitational encounters and trajectory adjustments, and decades of travel through the outer system's darkness finally give way to the true interstellar journey, the path it will follow, not for decades, but for millennia, not through our solar system, but through the galaxy itself, moving toward a destination we can describe in technical terms, but that represents, in practical reality, an exit into the unknown, a return to the interstellar medium from which it came, a continuation of a journey that was already ancient when it first entered the region of space we call home. Chemistry doesn't just disappear. It lingers, disperses, follows paths determined by forces we can model, but that become increasingly complex as scales increase and timescales extend. When 3I Atlas outgassed during its approach to the Sun, when solar heating warmed its surface and released methanol and cyanide and other volatile compounds into space, those molecules didn't vanish. They formed a cloud around the comet, a temporary atmosphere of ejected material, and as the comet continued its journey, as it moved through space trailing that cloud behind it, the molecules spread out, creating a wake, a chemical trail that marks the path the object followed, a signature that persists in the interplanetary medium long after the comet itself has traveled millions of kilometers away. That wake is real, measurable, a physical trace of 3I Atlas's passage through our solar system. Spectroscopic observations during the comet's active period detected those molecules, identified their presence, measured their abundances and velocities. Scientists mapped the outgassing patterns, understanding how material was released from the nucleus, how it expanded into space, how solar radiation and pressure shaped the resulting cloud. But those observations captured only a snapshot, a moment in time when the comet was close and active and bright enough for detailed study. What happens to those molecules over the months and years that follow, as they disperse across millions and billions of kilometers, as they mix with the ambient environment and become increasingly difficult to detect? That's a question that requires different observational strategies and raises fascinating possibilities about long-term chemical transport in space. Molecules in space don't travel in straight lines. They're affected by solar wind, by radiation pressure, by gravitational fields, by electromagnetic forces that can accelerate charged particles or alter trajectories in subtle ways. Methanol molecules released from 3I Atlas during its perihelion passage experience all of these influences. Some get ionized by solar ultraviolet light, acquiring electric charge that makes them responsive to the sun's magnetic field, causing them to spiral along field lines or be accelerated outward by solar wind. Others remain neutral, moving on ballistic trajectories determined by their initial velocity and the weak but persistent pressure of sunlight pushing against their molecular structure. The result is a dispersing cloud, a complex three-dimensional structure that expands and deforms and gradually loses coherence as different molecules follow different paths, spreading across space until the concentrations drop below detectable thresholds, and the wake effectively vanishes into the background chemistry of the solar system. But even at undetectable concentrations, even when dispersed so widely that no telescope could measure their presence, those molecules still exist, still contribute to the solar system's chemical inventory, still move through space, carrying the signature of their origin in an interstellar visitor. And occasionally, perhaps, they reach destinations. A methanol molecule released from 3I Atlas in late 2024, pushed outward by solar radiation pressure, carried by solar wind, following a trajectory that happens to intersect with Earth's orbit months or years later, could enter our atmosphere, could be swept up by our planet's gravitational field, could become part of the constant rain of interplanetary material that falls on Earth every day. Tons of material delivered from space, most of it dust and particles too small to notice, but all of it contributing chemistry, adding molecules, integrating material from beyond Earth into our planet's surface and atmosphere and biosphere. The same process could deliver material to Mars, to the moons of Jupiter or Saturn, to any body whose orbit happens to cross paths with the dispersing wake of molecules left behind by the comet. The probabilities are small, the amounts of material minuscule, the concentrations so diluted that detecting 3I Atlas-specific molecules in Earth's atmosphere or on another world's surface would be nearly impossible. But the process occurs nonetheless, a form of chemical exchange operating on solar system scales, connecting the paths of interstellar visitors to the worlds they pass, creating links between chemistry originating in distant stellar systems and environments that might eventually host life or already do. Could fragments separate from the main body? Could pieces of 3I Atlas break off during its journey, following slightly different trajectories, becoming independent objects that might reach different destinations or impact different worlds? It's possible. Comets are fragile, held together by ices and weak gravitational self-attraction, subject to stresses as they heat and cool, as tidal forces from nearby planets stretch and compress their structure, as outgassing creates jets that push against the surface. Fragmentation events aren't rare. We've observed comets breaking apart, splitting into multiple pieces that drift slowly away from each other, each following its own trajectory, each potentially reaching a different fate. Borisov showed signs of fragmentation, small pieces separating from the main nucleus, too small to track individually, but evident in observations showing the brightness distribution didn't match a single solid body. If 3I Atlas fragmented, if pieces separated during its perihelion passage, or during the later stages of its journey through the inner solar system, we might not have detected it yet. Small fragments are difficult to observe, too faint to register, except in the most sensitive instruments, easily lost against the brightness of the main nucleus when the comet is active and surrounded by outgassing material. But as time passes, as the main body moves further away and observational conditions change, fragments could become visible, could be detected as separate objects following slightly different trajectories, spreading out along the comet's path, creating a trail of debris rather than a single cohesive body. Monitoring for such fragments is part of the ongoing observation strategy, part of the reason scientists continue tracking 3I Atlas even as it fades and distance increases, because surprises occur, because what appears to be a single object sometimes reveals itself as multiple bodies, and each piece potentially tells a different part of the story, carries different chemistry, follows a path that might intersect with different destinations. Radio telescopes play a crucial role in this monitoring, detecting emissions across wavelengths that aren't affected by visible brightness, that can pick up signals from molecules in space, that might reveal activity or chemistry invisible to optical observations. Spectroscopic analysis continues as long as the object remains detectable, searching for changes in composition, for evidence of new materials being exposed as surface layers erode, for any indication that the chemistry we measured during initial observations doesn't represent the complete picture. And infrared observations, particularly from space-based telescopes that avoid atmospheric interference, track thermal emissions, measuring how the object radiates heat, how its temperature changes with distance from the sun, how its physical structure responds to the thermal stresses of transitioning from warm inner system to cold outer reaches. All of this monitoring, all of these observations, serve a dual purpose. On one level, they're about understanding 3I Atlas specifically, about characterizing this particular object, about building a complete picture of its composition and behavior and trajectory. But on another level, They're about building a catalogue of knowledge about interstellar visitors in general, about understanding what's typical and what's unique, about establishing baselines that will help us interpret the next object that comes through, and the one after that. Because 3i Atlas isn't the last interstellar visitor we'll see. It's just the latest in what we're beginning to realize is a steady stream of objects passing through our solar system, most too small or too distant to detect, but occasionally close enough and large enough that we can study them, can learn from them, can add them to the growing database of information about what travels between the stars and what that traffic tells us about the galaxy we inhabit. The breadcrumb trail that 3i Atlas leaves behind, the chemical wake and potential fragments, and the trajectory data that traces its path through our solar system, all of it contributes to that database, all of it adds value to our understanding, all of it matters not just for what it tells us about this one object, but for what it reveals about the processes that shape interstellar space, that govern chemistry and motion and behavior across scales we're only beginning to explore. And that brings us to the real answer, the destination we've been approaching throughout this entire journey, the place where 3i Atlas is actually going, not in terms of specific dates or orbital positions, but in terms of ultimate trajectory, final direction, the path it will follow, not for years but for millennia, as it leaves our solar system behind and returns to the interstellar medium from which it came. Let's be precise about this, because precision matters when we're talking about objects traveling at interstellar velocities through gravitational fields that extend across billions of kilometers. 3i Atlas is on a hyperbolic escape trajectory. That's not speculation or approximation. That's confirmed observational fact. Trajectory data collected from multiple observatories, velocity measurements refined through months of tracking, orbital elements calculated with the precision modern astrometry allows. The object entered our solar system from interstellar space, fell inward toward the Sun, passed through perihelion, and is now on an outbound path carrying enough velocity to escape the solar system permanently. It's not coming back. It's not on an elliptical orbit that will loop around and return in some future century. It's leaving, forever, following a trajectory that will carry it away from our Sun and back into the galaxy. Where exactly is it going? That requires defining what we mean by where when we're talking about interstellar journeys. In terms of direction, 3i Atlas is moving outward through the solar system toward a specific region of the sky, a direction we can describe using galactic coordinates, pointing toward a section of the Milky Way that lies in a particular constellation as viewed from Earth, heading toward a destination that's less about reaching a specific star and more about the general direction of travel through the galactic neighborhood. The closest star in that approximate direction is light years away, a distance that even traveling at 3i Atlas's velocity would take tens of thousands of years to traverse. The object isn't aimed at that star specifically, isn't on a trajectory that would result in a close approach, but it's moving generally in that region of the galaxy, heading outward from the Sun toward spaces where other stellar systems exist, where the interstellar medium continues, where the journey that brought it here will continue in reverse, moving from our stellar neighborhood back into the broader galactic context. The direction isn't random. It's determined by the trajectory 3i Atlas followed on its inbound journey and the gravitational deflection it experienced passing around the Sun. Objects on hyperbolic trajectories don't exit the solar system in arbitrary directions. They follow paths shaped by conservation of energy and momentum, by the angle of their approach and the speed they carried entering the system, by the gravitational influence of the Sun bending their trajectory during perihelion passage. Think of it as a slingshot effect, not gaining energy from the Sun's rotation like spacecraft do from planetary encounters, but following a curved path determined by the gravitational field, entering on one trajectory and leaving on another, with the difference between those two directions determined by how close the perihelion approach was and how the gravitational geometry worked out. Now, Jupiter's potential influence complicates this picture slightly, adds uncertainty to the specific direction 3i Atlas will ultimately follow. If the March 2026 encounter produces measurable gravitational effects, if the object's path bends during that proximity to Jupiter, the outbound trajectory could shift, could point toward a slightly different region of the galaxy than current models predict. The shift wouldn't be enormous, not a complete reversal of direction, but potentially significant enough to alter where the object would be tens or hundreds of thousands of years from now, which stars or stellar systems its path might eventually bring it near, whether its journey takes it above or below the galactic plane, or continues roughly within the disk where most stellar material concentrates, the uncertainty margins in these predictions are larger than most people realize. We know the general trajectory very well, know the object is leaving and approximately which direction it's heading, but the precise path, decades or centuries from now, depends on factors we're still measuring. Small uncertainties in current velocity measurements compound over time. Tiny forces we might not have fully accounted for, like outgassing events that produce thrust or radiation pressure effects that gradually alter trajectories, accumulate across the immense timescales and distances involved in interstellar journeys. By the time 3I Atlas is a light year from the Sun, by the time it's truly in interstellar space beyond any significant gravitational influence from our star, the uncertainty in its position could be measured in billions of kilometers, a volume of space large enough that pinpointing where exactly it will be becomes more about probability distributions than precise coordinates. But here's what we can say with confidence. 3I Atlas will cross the orbits of the outer planets over the coming decades, will pass through the Kuiper belt, and eventually reach the heliopause, the boundary where solar wind gives way to the interstellar medium, sometime late this century or early next, depending on exact velocity and how we define that boundary. That crossing represents, in practical terms, the moment when 3I Atlas stops being a visitor to our solar system and becomes an interstellar object again, returning to the state it was in before entering our stellar neighborhood, traveling through the sparse medium between stars, encountering the occasional dust grain or hydrogen atom, but otherwise moving through near-perfect vacuum, following a trajectory determined entirely by its velocity and the weak gravitational influence of the galaxy as a whole. Where does leaving the solar system actually mean? That's less clear-cut than it might seem. The Sun's gravity extends essentially forever, diminishing with distance but never truly reaching zero, so there's no sharp boundary where gravitational influence ends. The heliopause marks the point where solar wind is balanced by interstellar pressure, but objects well beyond that distance are still orbiting the Sun if they're on bound trajectories. The Oort cloud, the spherical shell of cometary material that represents the outermost extent of the Sun's gravitational domain, stretches to perhaps a light year or more, distances where orbital periods are measured in millions of years, where the distinction between orbiting and passing through becomes philosophical. 3I Atlas, on its hyperbolic trajectory, passes through these regions without being captured, continues outward even when technically still within the Sun's gravitational sphere of influence, and eventually reaches distances where galactic forces matter more than solar gravity, where the object's motion is determined primarily by its place in the rotating disk of the Milky Way, rather than by which star it happens to be near. The timeline extends beyond human lifetimes, beyond the span of civilizations, into timescales that challenge our capacity for meaningful comprehension. By the 2040s or 50s, 3I Atlas will be beyond Uranus. By the late 2000s, possibly beyond the heliopause. By the year 3000, it will be light years away, further from our Sun than the nearest stellar neighbors, traveling through true interstellar space with no reasonable prospect of ever returning, no mechanism that could bend its trajectory back toward the solar system it left behind. By 10,000 CE, if we could somehow observe it, if we had telescopes powerful enough to detect an object that's small and cold and distant, 3I Atlas would be a wanderer again, moving through the galaxy, as it presumably did for millions of years before encountering our Sun, carrying with it the chemistry it accumulated in whatever stellar system gave it birth, the methanol and cyanide and organic compounds that tell stories about nebular chemistry and planetary formation processes operating in regions of the galaxy we've never visited and likely never will. And eventually, maybe, it encounters another stellar system. Not soon, not within any time frame relevant to human civilization as we know it, but given enough time, given the scale of the galaxy and the number of stars and the randomness of trajectories, any object on an interstellar path will eventually pass near something, will swing past another sun, will have the opportunity to either be captured into orbit if conditions align perfectly, or more likely to pass through, receiving another gravitational deflection, continuing its journey on an altered trajectory, moving from system to system over millions of years, a traveler without destination, a carrier of chemistry and history, and the accumulated effects of every gravitational encounter along the way. That's where 3I Atlas is going. That's the answer to the question we posed at the beginning of this journey. Not to a specific coordinate or a named star or a destination marked on any map, but into the galaxy, into interstellar space, into regions beyond our ability to track or observe or influence, carrying its mysteries with it, leaving behind questions about its origin and chemistry, and whether anything about its trajectory was more than coincidence. Questions that might never have definitive answers, but that change how we think about the objects moving through space, about the traffic between stars, about our place in a galaxy far more dynamic and interconnected than we often imagine. So why does this matter, and what does it mean for how we understand our solar system's position in the larger cosmic context? We're not alone in receiving visitors. That might be the single most profound realization emerging from the detection and study of interstellar objects like 3I Atlas. Not alone in the sense of intelligent life, not claiming that these objects represent communication attempts or deliberate messages, but alone in the simpler, more fundamental sense of being an isolated stellar system, sitting in empty space with nothing moving through it except the material that formed here, the planets and comets and asteroids that were born in our solar system's primordial disk. That isolation was always an illusion, a product of observational limitations rather than reality, but it's an illusion we lived with for most of human history, assuming that space between stars was truly empty, that interstellar objects were so rare that we'd never detect them, that our solar system was essentially a closed system with clear boundaries separating inside from outside. Oumuamua shattered that illusion in 2017. Borisov confirmed it in 2019. Now, 3I Atlas reinforces the pattern, demonstrating that interstellar visitors aren't anomalies but regular occurrences, objects passing through our stellar neighborhood frequently enough that with proper observational capabilities, with survey telescopes scanning the sky consistently, and analysts trained to recognize unusual trajectories, we can expect to detect several per decade, perhaps more as our instruments improve and our search strategies refine. The galaxy is full of this material, full of objects ejected from stellar systems during planetary formation, comets kicked outward by gravitational interactions with giant planets, fragments of protoplanetary disks scattered into interstellar space by the same processes that create solar systems like ours. We're not special in producing this material, and we're not isolated from receiving it. We're part of a galactic ecosystem where matter circulates, where chemistry moves between systems, where the boundary between our material and foreign material is porous and constantly being crossed. What does the trajectory of 3I Atlas tell us specifically? It tells us that these objects follow predictable physics, that they're not maneuvering in ways that suggest propulsion or guidance, that their paths through our solar system match what we'd expect from gravitationally determined trajectories shaped by natural forces. That might seem disappointing to anyone hoping for evidence of artificial objects or interstellar probes, but it's actually valuable information, narrowing the field of possibilities, establishing baselines for what natural interstellar visitors look like, giving us reference points for future objects that might behave differently. If we ever do detect an interstellar visitor that doesn't follow expected trajectories, that shows signs of course corrections or unusual accelerations, we'll recognize it as anomalous because we've studied objects like 3I Atlas and know what normal looks like. But trajectories tell only part of the story. Chemistry matters equally, perhaps more, because chemistry reveals origin, reveals the conditions under which an object formed, reveals what stellar nurseries in other parts of the galaxy were producing billions of years ago when these objects were born. The methanol and cyanide detected in 3I Atlas's spectrum aren't random. They're indicators of specific formation environments, specific temperature and pressure, and chemical conditions that existed in the protoplanetary disk where this material accumulated. Different stellar systems produce different chemistry based on their metallicity, their distance from the galactic core, the age of the material forming planets, the presence of nearby massive stars whose radiation and supernovae enrich the local environment with heavy elements. By studying the chemistry of interstellar visitors, we're essentially sampling other stellar systems without ever traveling to them, collecting data about conditions in distant parts of the galaxy, building a database of how planetary formation chemistry varies across different stellar environments. The combination of trajectory data and chemistry creates a more complete picture. Trajectory tells us where the object has been and where it's going, what path it followed through our solar system, whether anything about that path suggests purpose or intentionality. Chemistry tells us about origin, about the stellar system that produced this material, about whether the compounds present are what we'd expect from standard nebula chemistry, or whether there's something unusual, something that demands explanation beyond simple formation models. When both trajectory and chemistry fit expectations, when everything about an object matches what we'd predict for natural interstellar debris passing through our system, we can be reasonably confident that's what we're observing. But if either trajectory or chemistry shows anomalies, if behavior doesn't quite fit models or compounds appear in combinations that seem improbable, the questions deepen, the investigation extends, and we confront the possibility that our models are incomplete or our assumptions about what's natural need revision. For 3I Atlas specifically, the verdict remains open. The trajectory appears natural, following a hyperbolic escape path determined by gravitational physics, with no clear evidence of course corrections or unusual accelerations beyond what outgassing might produce. The chemistry is interesting, methanol and cyanide in amounts worth noting, but not necessarily anomalous, not clearly outside the range of what stellar nebula chemistry could produce. The timing of the Jupiter encounter is intriguing, the possibility of gravitational influence, redirecting the object toward interesting destinations like Europa, is worth considering. But without evidence of actual course changes or deviations from predicted paths, it remains speculation rather than conclusion. We're watching, observing, gathering data that will either confirm or refute these possibilities, and in a few months, when the Jupiter encounter has passed and trajectory data shows whether anything unexpected occurred, we'll have better answers, clearer understanding of whether 3I Atlas is purely a natural object on a random path, or whether there are patterns worth investigating further. What about the future? What does 3I Atlas tell us about what to expect as more interstellar visitors arrive? It tells us we need better detection capabilities, better systems for identifying these objects early in their approach so we have more time to study them, more opportunity to gather spectroscopic data and trajectory measurements before they fade into the distance. It tells us we need coordinated observation strategies, multiple telescopes tracking simultaneously, radio and optical and infrared instruments, all focused on the same target to capture different aspects of behavior and composition. It tells us we need theoretical frameworks that can accommodate both natural objects and potentially artificial ones, that can distinguish between mundane explanations and genuinely anomalous behavior without dismissing either possibility prematurely. And it tells us something deeper, something about our place in the galactic context, about Earth's position not as an isolated world, but as one node in a vast network of stellar systems connected by the material that moves between them, by the chemistry that circulates through the galaxy, by the objects that carry information and compounds, and the history of formation processes operating across billions of years of cosmic evolution. We're downstream recipients of this material, catching occasional visitors that originated elsewhere, learning from them, studying their chemistry, tracing their trajectories, and in doing so, connecting ourselves to stellar systems we'll never visit, to regions of the galaxy too distant for our spacecraft to ever reach, but close enough that their cast-off material, their ejected comets and planetary debris, occasionally passes through our neighborhood and gives us a glimpse of what conditions are like elsewhere in the Milky Way. 3I Atlas is leaving, continuing a journey that started long before it reached us and will continue long after it's beyond our ability to observe. But its passage through our solar system matters, adds to our understanding, contributes data that will inform how we think about interstellar objects and galactic chemistry and the processes that connect stellar systems across vast distances. We witness something rare, something that most humans never experience. The passage of an interstellar visitor close enough to study, close enough to characterize, close enough to wonder about and question and imagine possibilities that stretch beyond simple physics into deeper questions about purpose and randomness, and whether the universe operates entirely on chance or whether patterns emerge, whether connections exist that we're only beginning to recognize. December 19th isn't goodbye. It never was. It's a milestone, a moment of closest approach, but the story continues beyond that date, through the months and years and decades that follow, as 3I Atlas moves through the outer solar system and eventually crosses back into interstellar space, carrying its mysteries with it, leaving us with questions that might take years or decades to answer fully, questions about its origin and its chemistry, and whether its trajectory through our system was entirely random or whether, just maybe, there was something more deliberate in its path, something we haven't quite figured out yet but that future observations might reveal. If you've stayed with me through this entire journey, If you've followed 3I Atlas from its December approach through the gravitational complexities of its outbound trajectory and into the vast distances of interstellar space, I want to hear from you. Drop a comment telling me what you think. Is this purely physics? Or do you see patterns worth investigating further? Are we watching random cosmic debris, or is there something about the chemistry and timing and trajectory that hints at deeper structure? Where are you watching from? And what questions about interstellar visitors matter most to you? Hit that like button if this changed how you think about objects moving through our solar system. Subscribe, because this story isn't over, because as new data comes in and our understanding evolves, we'll be following every development, every unexpected turn in a narrative that connects us to the galaxy in ways we're only beginning to appreciate. We're living in an era when the boundary between our solar system and interstellar space is becoming transparent, when visitors from other stellar systems pass through regularly enough that we can study them, when the chemistry circulating through the galaxy occasionally delivers itself to our doorstep for analysis. 3I Atlas is just one example, one data point, in what will eventually be a comprehensive catalogue of interstellar objects and their characteristics. But it's an important example, a well-observed case that adds to our foundation of knowledge, that helps us understand what's typical and what's unusual, that prepares us for the next visitor and the one after that, and the ongoing stream of material that moves between stars, connecting us to the broader galactic ecosystem. Whether we fully comprehend that connection or not, the journey continues. The questions remain, and somewhere out there, beyond the orbit of Jupiter, beyond the realm where planets orbit close together and the sun still dominates the sky, 3I Atlas moves outward, following a trajectory we've mapped but not fully understood, carrying chemistry that fascinates and puzzles us, heading toward destinations we can describe in coordinates but not truly comprehend. A traveler from beyond our world, returning to the interstellar void, and we're left watching, wondering, and waiting to see what the universe reveals next.